Legs work in a variety of terrains, but they are more difficult to build and control, and they can carry a significantly less heavy load. Optical character recognition is recognizing printed or written characters from their images. This is more natural than barcodes because no extra coding, in terms of bars, is used. If a single font is used, there is a single way of writing each character. There are standardized fonts such as OCR-A defined specifically to make automatic recognition easier. With barcodes or single font, a single template exists for each class and there is no need for learning. For each character, we have a single prototype that we can simply store. It is the ideal image for that character, and we can compare the scene input with all the prototypes one by one and choose the class with the best matching prototype. This is called template matching. There may be errors in printing or sensing, but we can do recognition by finding the closest match. If we have many fonts or handwritings, we have multiple ways of writing the same character, and we cannot possibly store all of them as possible templates. Instead, we want to learn the class by going over all the different examples of the same character and find some general description that covers all of them. It is interesting that though writing is a human invention, we do not have a formal description of A that covers all A's and none of the non-A's. Not having it, we take samples from different writers and fonts and learn a definition of A-ness from these examples. But though we do not know what it is that makes an image an instance of the class A, we are certain that all those distinct A's have something in common, which is what we want to extract from the examples. We know that a character image is not just a collection of random dots and strokes of different orientations, but it has a regularity that we believe we can capture by using a learning program. For each character, we see examples in different fonts, for printed text, or writings for handwritten text, and generalize. That is, we find a description that is shared by all the examples of a character. A is one way of combining a certain set of strokes. B is another way, and so on. Recognition of printed characters is relatively easy with the Latin alphabet and its variants. It is trickier with alphabets where there are more characters, accents, and writing styles. In cursive handwriting, characters are connected and there is the additional problem of segmentation. Many different fonts exist and people have different handwriting styles. Characters may also be small or large, slanted, printed in ink or written with a pencil, and as a result, many possible images can correspond to the same character. Despite all the research, there is still no computer program today that is as accurate as humans for this task. That is why CAPTCHAs are still used. A CAPTCHA being a corrupted image of words or numbers that needs to be typed to prove that the user is a human and not a computer program. Matching model granularity. In machine learning, the aim is to fit a model to the data. In the ideal case, we have one single global model that applies to all of the instances. For all cars, as we heard in Chapter 2, we have a single regression model that we can use to estimate the price. In such a case, the model is trained with the whole training data and all the instances have an effect on the model parameters. In statistics, this is called parametric estimation. The parametric model is good because it is simple. We store and calculate a single model, and it is trained with the whole data. Unfortunately, it may be restrictive in the sense that this assumption of a single model applicable to all cases may not hold in all applications. In certain tasks, we may have a set of local models, each of which is applicable to a certain type of instances.